Earlier on in organic chemistry, you would have learned what an allylic and a vinylic position is. And we're going to talk about a benzylic position in this video. And if you're wondering what a benzylic position is, well, a carbon that's directly attached to a benzene ring, we call those carbons a benzylic position. So we would say in this case, with this molecule, we have a benzylic carbon here and we have a benzylic carbon here. Now you might remember the aromatic rings and alkyl groups are both stable when it comes to chromic acid. So you can see here that if we take benzene and treat it with chromic acid, we get no reaction. And if we take this molecule here, so this would be heptane, if we treat that with chromic acid, we get no reaction. However, if we have a benzylic carbon and we have a proton on that benzylic carbon, we can get an oxidation reaction occurring when we treat it with chromic acid. And that's what we see right here. We see that this carbon is a benzylic position and it happens to have not one, but two protons attached to it. And so when we treat that with chromic acid, so that's generated from sodium dichromate, sulfuric acid, and water, we end up forming benzoic acid in this case. So we convert the blue carbon into a carboxyl group. Now, if you're wondering, what happens to the rest of it? Where does this go? Well, this just ends up in the waste, in the chemical waste. We say it's excised from the compound. So no need to worry about the byproducts. Now, like I said, the benzylic position needs to have at least one proton attached in order to undergo oxidation. So if we take a look at this carbon here, we can see that this carbon is quaternary. It has no hydrogens attached, and therefore we get no reaction. Now, besides using chromic acid, we can also use potassium permanganate. And you can see here, this is a two-step process. In the first step, we treat our benzylic position. So again, this one has two protons, so it's going to be susceptible to benzylic oxidation. We treat it with potassium permanganate in water, and we heat that up. We end up with a carboxylate in this case, carboxylate. This would be potassium benzoate. And then in the second step, we do a workup with aqueous acid to add the proton to that oxygen that was negatively charged, and we end up with our carboxylic acid. Now, besides oxidation, benzylic positions can also undergo a bromination. They can undergo what we call a benzylic bromination, which is a type of free radical bromination. So again, if we have a benzylic proton, okay, at our benzylic position, and we treat it with NBS, and you might remember that NBS is N-bromosuccinimide, okay? What that does is it replaces the proton with a bromine. So now we have a benzylic bromide. And what's cool about benzylic bromides is that they're very useful in synthesis. And we've actually seen them before in organic chemistry. First of all, a benzylic bromide, like the one that's shown right here, would easily undergo an SN1 substitution. Now, why would that happen so easily or so readily? It's because, remember, the first step in an SN1, it's SN1 at a time. The first step would be the loss of leaving group, and the second step would be the nucleophilic attack. So once this leaving group leaves, I don't have a lot of space here, but what you would end up with would be a benzylic carbocation like this, and you could draw three more resonance contributors for this. So since it's highly resonance stabilized, it's very easy for that bromide to leave. Then our water comes in as our nucleophile, and after a proton transfer, we end up with this tertiary alcohol. Unhindered benzylic bromides, on the other hand, they can undergo an SN2 substitution that we see here. This compound is called benzyl bromide. Benzyl bromide. The reason I bring the name up is it's used as a synthetic intermediate quite a bit in organic chemistry. So you can see we're just doing a straightforward SN2 reaction, nucleophilic attack, and loss of leaving group. And now we're ending up with a primary alcohol in this case. Now, what about elimination? Benzylic bromides can also undergo an elimination. You see here we take this tertiary benzylic bromide. This is our alpha carbon. This is a beta carbon, and it has three protons. I'll just draw one for instructional purposes only. When we treat that with an unhindered base like sodium ethoxide, the ethoxide is going to be able to rip that proton off. We form our double bond, and we lose our leaving group like that. So there's our E2 reaction. And in the process, we form ethanol and sodium bromide. Furthermore, if we take a benzylic alcohol and treat it with concentrated sulfuric acid, that can do an E1 reaction, right? The first step is going to be protonation to convert the hydroxyl into a good leaving group, an oxonium ion, and so it's going to leave. And then we end up with that benzylic carbocation that we saw in a previous slide, which is highly resonance stabilized, and then water comes in as a base and rips off a proton to give us our alkene. And so now we have a bunch more possibilities or tools in our synthetic toolbox, okay? Now we know how to do oxidations at the benzylic position to make a carboxylic acid. Later on, we're going to do an entire chapter where we study carboxylic acids. But we can take our benzylic bromides and we could convert them into alcohols or alkenes. Once you have an alcohol, you can go back to chapter 12 and look at all the different reactions we did in there. Or with an alkene, you can go back to chapter 8 and look at all the different reactions we did there. And so this question says, draw the expected product when each of the following compounds is oxidized with chromic acid. So if we were to take toluene and treat it with sodium dichromate, sulfuric acid, and water, keep in mind there's 3 benzylic protons here. I'm just going to draw one in, so that means that this carbon is going to be susceptible to benzylic oxidation. And so in this case, we would just oxidize that one carbon, and so we would end up with this compound, which is benzoic acid. In the second one, same thing. We're going to treat it with sodium dichromate, sulfuric acid, and water to make our chromic acid. Now we've got a benzylic position here with a proton. We've got a benzylic position here with a proton. And so we're going to end up with a dicarboxylic acid. So we're going to have a carboxyl group at this position. And we're going to have one meta to it as well. All right. And for the last one, you notice that we have 3 different groups here. But you notice that only this one and this one have benzylic protons. There are no benzylic protons on this carbon, and so that tert-butyl group is not going to undergo oxidation. And so when we take this compound and we treat it with our sodium dichromate, you can practice writing this out, what we're going to end up with is we're going to end up with a dicarboxylic acid. So we're going to have a carboxyl group in this position and in this position. But the tert-butyl group is going to remain intact and it will be unoxidized. Okay, let's try a couple of synthesis problems that involve benzylic bromination. So for the first one, we're taking toluene, and then we want to install this nitrile. Remember, this is CN group here. We call that a nitrile, and that could come from benzyl bromide. If we had the benzyl bromide, and now all we'd have to do is treat it with sodium cyanide, right? Sodium cyanide, right? Na plus and Cn minus, right? So cyanide is a good nucleophile. So we know how to convert the toluene into the benzyl bromide. All we have to do is treat it with NBS, and so NBS, and we're going to heat that up a little bit. And then in the second step, we would use our sodium cyanide as our nucleophile to come in and do our SN2 reaction. In the second one, we're adding a methoxy group here, so we're synthesizing an ether, really, is what we're doing. But keep in mind that this carbon is attached directly to the aromatic ring, and so this proton is a benzylic proton. And so if we could make this compound, so if you just bear with me while I sketch it out, if we could make this tertiary alkyl bromide like that, right, then that would be susceptible to an SN1. And so we could just use methanol, CH3OH, as our solvent, and that would do just a solvolysis reaction. And so in order to make the compound that I have here in the green box, all we're going to need is NBS and heat, same as the first problem. So first step will be NBS, and we'll use the triangle for heat. And then in the second step, we're just going to need some methanol as our solvent, and that would be an SN1 reaction. Again, that would be an SN1 reaction. All right, next one is kind of a cool one. I like this one because you're actually losing a carbon. If you notice very carefully, the starting material has 6, 7, 8, 9 carbons, but the final product has 6, 7, 8 carbons. And so you can see where this is going. in order to make that carbonyl, you'd want to do an ozonolysis reaction. And so if you could make this compound, so just bear with me here. If you could make this compound and then do an ozonolysis right here, then you would end up with this compound, which is acetophenone. And we know the common name of that compound. And so how could we do that? Well, we could make that from, if we had the alkyl halide, right? Or sorry, the benzyl halide, my mistake. If we had this compound, right, then we would just do an E2 reaction using an unhindered base like sodium methoxide. And so how would we make that compound? Well, benzylic bromination, same as the other two problems. And so our first step is going to be NBS, and we're going to heat that up. Then we're going to treat it with sodium methoxide to do our E2 and make our alkene, so to make this compound. And then the last step is going to be the ozonolysis of an alkene. And so that's a two-step process. The first step is DMS, or sorry, the first step is ozone, Mr. Dion. Ozone, followed by the last step is DMS. And there you have it. A little bit of synthesis where we employ benzylic bromination in all of these.